Hello everyone. In this video we are going to talk about the sparse matrices. So many times you are dealing with matrices that have lots of zero elements, and those zero elements do not necessarily carry any information, but of course when you want to store them they need some disk space, right? They need memory. And when you are using those zeros, let's say in matrix multiplication, addition, or anything, although they are zeros, but you have to still operate all of those arithmetics on them. So basically, they are adding to the computation load and to the memory requirements without doing anything, right? So let's say you have a system of equations, and the system of equations is something like this. You have 10 variables and 10 equations in a linear format. And if you look at this, you see that not all variables are showing in all equations, only a few of them do. So if you want to look at the coefficient matrix for this set of equations, that's this guy here. And if you see in each row, there are only one, two, or maybe three numbers that are non-zero. So, and this is the right-hand side. So here, if I want to basically store matrix A, I have to type in all of these zeros, right? So that's one thing you have to do. And of course, you can use the backslash operator to solve the equation, right? So here, what I want to show you is one way is, of course, I define this matrix A, correct? And you see, it's a 10 by 10 double. Now, another way to store the information in A is just to store where the non-zeros are happening. So just store the values and the locations and forget about all the zeros. And this is how we create a sparse matrix. So here, I'm going to convert that A matrix into a sparse matrix and call it A sparse. Okay, so let me go ahead and do that and you can see the difference. So here, I'm going to run it. And now if you look, let me move up a little bit. So A sparse has only these guys in it. And if you can see, like, and I show you a command to find how many of these are non-zero, but you see only those non-zero values, right? And the row and column index are showing here, not 100 numbers, because A is 10 by 10. So instead of 100 numbers here, I'm just using a fraction of that, something between like 10 to 20, correct? And if you want to know, by the way, how many non-zeros are in a sparse matrix, this command called nnz, so you can apply to a sparse matrix and it returns the number of non-zero elements. So all I need is to apply that nnz to sparse, right? So I say nnz of a underscore sparse, and you see it was 22. Yeah, I thought it's less than 20, but it was actually a little bit more than 20. Still, 22 out of 100 numbers is all you need to store. And you might say, well, you have to store all these locations and all these numbers. Would this A underscore sparse, would that allocate less memory than A does? And all you need to do is to run the whos command. So say whos. And you see, guess what? A is 800 bytes, while A sparse is only 440. Yes, about half of the memory size is taken for that. And the same goes for operations. When you apply operations, there are algorithms for any operation like multiplication or anything that might be a lot easier to operate than basically to do the full matrix and just keep multiplying all these zeros by whatever number it is to get the answer. So in terms of arithmetic, also it makes it a lot more basically, I would say, efficient to use sparse matrices. Okay, so first thing we learned is how to convert a matrix into a sparse. If it has a ton of zeros, we use the command sparse. If we want to know how many non-zero elements it has, we use the command nnz. And by the way, the ratio of these non-zeros, right? The ratio of non-zeros to the total number is called density, and one minus that, which is the number of zero elements to the total number of entries, is called sparsity. So in this case, if you want to say what's the sparsity of this matrix, that's 1 minus 22 over 100. Okay, so that's 78%. So this matrix is 78% sparse, or 78% of the entries are zero, or the density of it is 22%. Okay, so density is the number of, the fraction of entries that are non-zero, the fraction that are zero, we call it the sparsity. Okay, so just keep that in mind. Now, if you want to know which elements are non-zero in the matrix, there is also this command, non-zeros. So if you pass non-zeros to a sparse matrix, then it will give you the values of the matrix that are non-zero. So in this case, these 1, 2, 1, 2, negative 3, we should be able to extract all of those. So let's go ahead and apply it here. So non-zeros of A underscore sparse. And you see, I could get all of those non-zero values. Okay, so n and z is the number of non-zeros. The non-zeros are the actual values. And if you want to know where, in which locations, in which rows and indices these entries are, then we can use the command that we know probably from matrices, and that is the command find. So if we just give it find, it gives me all the row locations, the column locations, and the values. So you see, find does better than non-zero. Not only it returns all of the values, it also returns the locations. Now here, if I don't care about the location, the values, just the locations, then I say maybe rows, right? And then columns, right? And then I don't care about the values. This is equal to find of A underscore sparse. And look here, if you can see, it shows me the row locations. So these are the rows, and then these are the columns of all of those non-zeros. So for instance, your first non-zero element is in row 6, column 1. The second one is row 10, column 1. The third one is similar, right? Row 1, and then column 2, and so on. So you can see the locations, you can see the values, you can see how many. And if you want to see it as a pattern, then we have this beautiful command called spy. So I can use the spy command, say, hey, show me the pattern of sparsity for this matrix. And then look, it shows it like this. And if I go back and put it side by side with A, you see that's exactly what it is. Look here, row 1, column 2, that's here. Right below it, row 2, column 2, that's there. Just next to it, that's negative 3. So in this 10 by 10 matrix, you see here 10 rows and 10 columns, right? In this square, if let me insert a rectangle here. So in this 10 by 10, which starts from here and goes all the way to there, in this guy, basically only those locations that they have a blue spot are non-zero. Everywhere else that is empty or blank, that is a zero. Okay, so this is called what? This is called the sparsity pattern. Okay, so now that we have seen these portions, let's move on and look at other things that are interesting. So one way to create the sparse matrix is if you have the full matrix and then use the sparse command on it and convert it to sparse. But can we just start with the sparse matrix right off the bat? The answer is yes, you can. Okay, how do you do that? Well, there are several ways you can do it. One is you have the rows and the columns where the entries are non-zero. You have those, and you have those non-zero values. So you just pass those rows, columns, and the values and the dimension of the matrix in general, and the sparse command will create it for you. So since I always use II and JJ, let me use what I'm always used to. Right? So I want to go to row 1, column 1, row 2, column 3, row 3, column 2, and put in values 10, 20, 30. Everywhere else in this 6 by 4 matrix, it's going to be all zeros. So let's go ahead and do that. So we're going to run these commands, and here we go. You see my matrix is S1. If you look at it, it's a 6 by 4 sparse matrix. Okay, and clearly the dimension of it is 6 by 4, and it's not going to take as much space as an actual 6 by 4 does. Okay, so you see it only takes 88, and that's all it is taking. Okay, but if I did it with a bunch of zeros and just changed these 3 to 0 to non-zero, then you would definitely have more memory. Okay, so one way is going this way. Another way you can do it is the command basically for allocation. So you can create a matrix of that is sparse. You can give it dimension m by n, and then tell it how many non-zero values you think you will have. So you you allocate some space to it using the sp_alloc. And then you can start typing the entries one by one based on row and location like that. So let's say here I say I want a 10 by 20 matrix with only 12 non-zero values, call it S2. So if I run this, you see S2 is a 10 by 20 sparse matrix, all zeros right now. But as soon as I run this line of command, now it goes to position 3 and 4 and plug in a 6 for me. You see, it's added. Now I can add another non-zero somewhere else, right? Here and then here. There we go. You see, so, and then I can keep going and plug in all of the 12 numbers. Okay, so this one allows me to go in and define 12 non-zero matrices. So let's see if I go ahead and just plug in a few more, just make it 12, see if we go beyond 12, what's going to happen? So here I typed in 12 numbers, okay, all non-zeros, and had no problem. S2 is clearly a matrix of all zeros except for these 12. Now you might wonder what happens if I go ahead and add another non-zero like that, right? So now I want to give the 13. And you see that it did not pick anything on me, right? So you see that's 4, that's 8, that's 13. So if I go above that, would that change anything? No. If I do a whos, you see S2 is well defined, is 10 by 20, and if I run the command n and z on S2, it returns 13 and there is no problem. So you start allocating space for 12, but if you go above 12, you should not see anything. And if I use the command spy on this S2, correct? Let's see here if we have really 13. So that's 5, 6, 7, 8, 9, 10, 11, 12, 13. There we go. You see, it actually has no problem. Okay, so this is so far, some basics. And so we learned different ways, 3 different ways, by either allocation and typing the entries by location, or by the command sparse to begin it and pass all the information in one line, or define the full and then convert it to sparse. So there are 3 different ways to define it. Now you might wonder, is there a way to go back? So if I have a sparse matrix, can I convert it back to the full matrix? And the answer is yes. The command is called full. So for instance, this S2, which was a 10 by 20 with a bunch of zeros, can I see the full version of it? So I just say full S2. Look. And here, this is the 10 by 20 with a ton of zeros and only 13 non-zeros. So you see the command full is working, and if I say whos, clearly the answer, which is what I assigned the full to, you see it is not a sparse matrix anymore. You see it doesn't have a sparse in front of it under attributes. It's a full matrix and clearly is not sparse, okay? Or if I give it some name, so I call it S2 full, right? So clearly S2 full is, if you look at it again, S2 full is clearly not a sparse matrix. Now, is there a command that I can check whether a matrix is sparse or not? The answer is yes, and as with any other logical command in MATLAB, they start with is. So is sparse of S2? You see the answer is yes. Is sparse of S2 full? The answer is no. Okay, so we can use a sparse command to check on those. Good. A few other useful commands, and that I mentioned here. So if you want to create special matrices that are sparse, right, like the identity matrix, a diagonal matrix, or random matrix, are there commands for that? The answer is, of course, there is. And so since I showed you all of this, let's look at some special sparse matrix commands. So you know the command I will create an identity matrix with that dimension, right? So 10 by 10 in this case. Now there is a sparse I, SPI, which creates a sparse matrix 10 by 10. So what's the difference? So look here, I say I equals I of 10 and I run the command. Okay, and you see I is a full 10 by 10 matrix with a ton of zeros. Now, if I say sparse is sparse I10, look, still it's a 10 by 10 matrix and still has all the ones on the diagonal, but it does not include all of those zeros. Okay, so you see I spy here is a 10 by 10, but the sparse double. So that's one. Can you do a diagonal that is not specifically identity matrix? And the command diagonal, MATLAB can create not only a just regular diagonal matrix, which has only non-zeros on the diagonal, main diagonal. If you give it an extra dimension, it can move those non-zeros to sub-diagonals, and you can even get tri-diagonals or anything like what I'm making right here. So at the main diagonal, I have values of 6, 7, 8, 9, 0, and let's just make it not 0, maybe 30. And then on the diagonal, place -1 below it, and then above it, I have these others. So this is what we call a tri-diagonal matrix, correct? So here, what I want to create is a sparse matrix, and dimension m and n for it are 5 by 5, or let's say, just to make it bigger, 8 by 8. So I'm going to make an 8 by 8 sparse matrix. And only this diagonal and these three major, the other two sub-diagonals are non-zero. Now, if I change this to 8 by 8, I have to make those dimensions also 8 by 8. Okay, so let me go back to 5 by 5 because I don't want to type more and take your time. So let's say it's just 5 by 5 and only these guys are non-zero at the diagonal above and below it. Which, how do I know above and below it? This dimension D would tell me that the first one goes to notation -1, 0 for second row, 1 for third row. And then this should create a sparse matrix. So let's go ahead and do that. Now, seems like I did not, oh, sorry. I have to go with this one. So let's define them, and then we have to run this command here. And there we go. You see, here is the matrix. These are all of those non-zeros that we define in B, and they are in the diagonal. Now, if you want to see the full version of it, we just passed it to the full command, and there we go. You see, that's your main diagonal, 6, 7, 8, 9, 30, and then above it and below it are those numbers. Now, of course, you can see that those numbers, you don't need 5 of that because the above and below main diagonal, you only have 4 numbers. So you see that 10 is clipped here. And then this 1, 2, 3, 4, that 5 is clipped, of course. Okay. But if you want to pass it to it, it has to be as a matrix. So you cannot have one row with 4 and the other row with 5. But just know that these two numbers will be clipped. So you see here, that is the full version of it. That was the sparse version of it. So I can make a sparse diagonal matrix and not just the identity matrix. And can I have random numbers, sparse random? Yes, the answer is command sprand. So you give it the number of rows and columns, and you give it the density. And remember, density is the number of non-zero values. So if I want 80% to be zeros, then the number I should pass it is 1 minus 0.8 or 0.2, 20%. Okay, then it will create a matrix of random numbers for me, let's say 6 by 8, with 20% non-zero numbers. So let's go ahead and do that. So here I run the command and, here, this one. There we go. So matrix is 6 by 8. I want 20% non-zero in it. And this is that. Now, if you want, I can display the full version of it for you, which is this guy. So this is the full version of that. You can see it's clearly 6 by 8, 6 rows, 8 columns. And now you might wonder, do I really have exactly 20%? The answer is not really. It depends on your dimension and depends on this percentage. If the result of this percentage multiplied by the total number of entries, which is 6 times 8 times density, would that be an integer number? If it is, then yes, you would exactly get that. If it's a decimal, you will not get that. In this case, you have 48 entries. 48 times 0.2 is going to be what? It's going to be 9.6. You cannot have 9.6 non-zero values. It has to be either 9 or 10. So if you look at this, clearly you can see there are 4 here and there are another 4 there, so it's 8. And of course, I can use the N and Z command, right? And here we go. You see, it gave me 8. And so if you run it again, you might get different numbers, right? So let's go ahead and run it one more time. Here we go. And you see, I still get 8. And again, this time I got like, looks like 10 this time. So if I call this on it, you see I got 10. So that number is not going to be exactly preserved. It's just going to be approximately those many non-zero numbers. Just keep that in mind because you're dealing with random numbers. So randomly you might get one of these as 0 as well, in addition to the rest of it. Okay, so hopefully that basic introduction so far was useful to you. You learned how to define a matrix that is sparse by different ways, how to go back to full if you want. You saw the advantage of a sparse matrix, which is taking less memory. And of course, some different commands, whether logical or processing and so on the sparse matrices. So before I finish the video, you might say, well, you told us that, yes, they need a smaller amount of smaller volume on the disk, right? Smaller memory. And we just saw that based on the number of bytes. But if you define this coefficient matrix here in this set of equation as a sparse matrix like this, can you still use that to solve this set of equations using this back// operator? You see here, if I use the back// operator, well, let's make sure that my A and B are defined properly because my B was defined down here differently, right? So let's go back and redefine them and use the back// operator. So you see, well, here, these are those solutions, right? These are the x1 to x10. Now, if I get a sparse at the sparse of A, can I still use this back// operator? So let's try that. So here we say solution maybe 1 or solution sparse maybe is A underscore sparse back/B. Would you get that? So let's go ahead and try it. And look at this. -4D45. And look at that. We just found above it, which is here, -4D45. So you see, MATLAB does allow you to use the back// operator regardless of use the sparse matrix or the original one. And if you run this command as opposed to this one, and your A is a very large matrix, this one is going to take smaller time to process than this one does. Okay, so hopefully now you see the value of it a little bit further. Thank you so much for your attention, and I'm going to see you in the next video. Thanks.